Welcome to our exploration of a technology set to redefine our digital world: quantum communication networks, or QCNs. These networks aren't just an upgrade, they promise a paradigm shift in secure data transfer and pave the way for entirely new quantum applications, all by harnessing the fascinating rules of quantum mechanics. At the very core of quantum communication are principles that seem straight out of science fiction. Take quantum entanglement. Imagine two particles linked so intimately that measuring one instantly tells you about the other, no matter how far apart they are. This is a cornerstone for many quantum protocols. Then there's superposition, where quantum bits, or qubits, can be both a 0 and a 1 at the same time, vastly increasing how much information they can carry. Crucially, there's the no-cloning theorem. This fundamental rule states you can't perfectly copy an unknown quantum state. Any attempt to eavesdrop on a quantum communication inevitably disturbs it, alerting the sender and receiver. This is a game-changer for security. We also have quantum teleportation, not of people, but of quantum states, moved from one place to another without physically sending the particle itself, relying on entanglement and classical channels. Building these networks relies on several breakthrough technologies. Quantum key distribution, or QKD, is the most mature right now. It allows two parties to create and share a cryptographic key that is provably secure. Any eavesdropping attempt on the photons used to transmit the key becomes immediately obvious due to the disturbance caused. For long-distance communication, we need quantum repeaters. Quantum signals unfortunately degrade over distance. Repeaters will help overcome this by creating and purifying entanglement over smaller network segments and then using entanglement swapping to establish end-to-end entanglement, effectively extending the network's reach. We also lean heavily on advanced photon sources and detectors to generate and read single photons reliably, and increasingly, on integrated photonics to shrink these components onto chips, making them more scalable, robust, and cost-effective. Don't forget quantum memory, crucial for storing quantum states and synchronizing operations. The potential applications are truly exciting. Enhanced cybersecurity is a major one. QKD offers the promise of virtually unhackable communication channels, vital for protecting sensitive data for governments, finance, healthcare, and critical infrastructure, especially against future harvest now, decrypt later threats from powerful quantum computers. QCNs will also enable distributed quantum computing, linking smaller quantum processors to create more powerful systems capable of tackling problems far beyond the reach of any single machine today. The ultimate dream is a global quantum internet, working alongside our classical internet to extend its capabilities, exchange quantum information, and support novel quantum applications. We can also expect breakthroughs in distributed quantum sensing, with entangled sensors achieving unprecedented sensitivities in medical imaging, environmental monitoring, or even improving earthquake detection. Secure cloud quantum computing, allowing sensitive data processing without revealing the data itself, and advanced cryptographic protocols like secure multi-party computation are also on the horizon. So, where do we stand? The field is advancing rapidly. QKD systems are already deployed in some point-to-point scenarios and small networks, being the most commercially developed aspect. However, a full-fledged quantum internet is still in its early days. Researchers globally are actively working to overcome challenges like extending communication distances, improving the efficiency and reliability of quantum repeaters, and developing robust quantum memories. Significant investments are fueling this second quantum revolution. The journey towards a quantum-enhanced future is well underway, likely starting with hybrid networks that combine the best of classical and quantum capabilities, making our communications fundamentally more secure and powerful.